AD tool is used to model and analyze the attack scenarios and build different defense strategies against those attacks. So our tool can be downloaded. The AD tool can be downloaded from the following link, and we have the downloadables in this section, and various other papers on this link. So before downloading the tool, the tool requires JDK 7 or the latest version to support the tool, because the tool is written in Java, therefore the environment is required to support the tool. Okay, because I have already downloaded the Java. To check the Java version, I need to write Java, and the version is written which is 11.0.8. So Java JDK can be downloaded from this link. Now for downloading the tool, we are taking the latest version of the tool, that is the beta version, and when we click here, the tool is downloaded and we save the file. Now the file is saved in the downloads. So to run the tool, we go to cd downloads, and then after typing this command java jar ad tool 2.2.0 full.jar, we press enter and the tool is processed with the Java running in the backend, and in the front end we can see the GUI of the tool. It is being downloaded. We can draw the sand tree, that is sequential conjunctive trees and trees, and then AD trees also. So AD trees are basically attack defense tree, so we can draw these trees. Okay, so we have file, we can load example trees, we can export the trees into XML, latex, PDF, PNG, JPG format, and we can import an XML file, an ADT, or any script, that is terms. Okay, we can print, and these are all the options. Now in edit window we have cut, copy, paste, and adding domain. These are basically the attributes on which we will going to evaluate the trees, and this is switch attacker or defender part. This option we can see later. Then in views we have themes, fit to window size, and windows, which window we want to view, the message log window, valuations view, ranking, or details view. Okay, so let's get started with the window. Now this is the root. For adding a child, we right click and we see these options, we add a child. Then if we want to add another child, we again right click, add a child. Now if we want to change the label, we write here child 2 and the label is changed. Child 1, and here we can add this description about the child, that what information does this child hold. Okay, even if we want to add into this term window, this is a script window and this is the tree window. So if we want to add another child, can add by writing this 3. If we want to validate, the child is added. Now this is the AND operation, that is to fulfill this attack, the root has to uh, take the child 1 path, child 2, and child 3 path. There is no option. Okay, and if we want to change the operator, right click and we change the operator. So this is the or path, that is it is optional for the root part to take child 1 path, or it can take child 2 path, or it can take child 3 path. So if we want to add a child here, we can add child here also. We had a countermeasure. Countermeasure is basically the defending strategy for this attack. So we can add the countermeasure here. Suppose we need to steal locker. So here we can say that we can pick a locker okay, and the defending strategy would be we can hide the locker. Suppose, just an example. Okay, so this can be the countermeasure for the steal locker steal. Okay, then we have these options: add a child, then fold above. If we say fold above, the tree gets folded, and this is the only view we can see. This is the only label we are able to see. Now if we say expand above, our whole tree is visible to us. So this is how we create a tree, and we can see the script over here. This is a term view. Okay, now we also have few example trees, so we can load the example tree. This is auction fraud attack, RFID DOS attack, communication block. So for instance, we can take communication block attack. Okay, so this is the term of this attack, and this is the tree. So we will expand this tree right now. Okay, now this is the tree we have for a blocking communication attack. That is, if we need to block a communication, the RFID communication, we need either to block the tag reader, or we need to block the reader backend. So by blocking the reader backend, for blocking the reader backend, we can implement DOS in the network. Okay, so the either attacker can take this path, or attacker can take this path. So for blocking the tag reader, we have several other paths. These are all optional paths, either this or this or this or this. So if we want to shield the tag, we have to follow both the path, then only we can shield the tag. So how can an attacker shield the tag? Be in the vicinity of the tag and implement Faraday cage. So cage around the reader and cage around the tag. Okay, so countermeasure for this is we can secure the warehouse. Okay, now here also we can say see some countermeasure, that jamming the signal, isolate the network, and secure warehouse, and secure Faraday around tag and reader. So for evaluating this graph, this is the graph we have built, which is already there in the example trees. Now this is the graph. Suppose we have taken into account how to block a communication. So this is the attack scenario. So for to evaluate this scenario, we have various domains, that is attributes on basis of which we can evaluate our tree, like custom domain on boolean values, custom domain on integer values, difficulty for proponent, that what how can we measure for the proponent, how can we measure for the opponent. So there are always two actors in the graph, that is for an attack, that is proponent or an opponent. So proponent is if it is an attacker, so the opponent will always be a defender. Okay, and if the proponent is defender, the opponent will always be an attacker. So this is vice versa. Okay, we can also calculate the minimal cost for the proponent. We can also calculate minimal skill level needed for the proponent. So these are all the attributes which can be evaluated for a particular graph. So here we can say probability of success. Let's see. probability of success. So initial value, let's check again that how the probability of success is calculated. Okay, so this is the proponent values and this is the opponent values. So if there is an or operation, opponent or for a proponent will be calculated by calculating the value of x adding to y and minus xy, and similar is the case for opponent. Then for an AND operation, both the values will be taken into account, and for a countermeasure the probability will be 1 minus x into 1 minus y. Okay, so this is the probability, if this is the probability of success, this is the probability of uh, this will be the probability of the failure, like opposite of the success. Okay, and the default value is assigned 0. Okay, so we have added this attribute, and after adding this attribute, this is the graph. So the default value assigned is 0 0. So the probabilities are based on two factors. Those are that what are the conditions required and whether the attacker will take this path or not. So these probabilities are basically based on various other scenarios. Here we will take just random values to calculate the overall probability of this graph. So for random values, we double click here, and this is the scale on which we can set the probability, and this is assigned that the value should be between 0 and 1. Okay, so this is the scale 0 to 1. So here suppose we have given the probability of securing the warehouse is 0.3. Okay, and here the probability is 3.6. Please remember these are only the random values. The actual values of an individual node is always calculated based on various factors, precondition and post conditions, and whether the attacker is taking that path. So what is the probability? So there are various other formulas and distribution metrics that can be followed for the probability. So here we are just taking the random values. So since we have assigned 0.6 to the this node, and 0.3 was the earlier probability, so the overall probability for this node is 0.42. Now we also assign the probability here just random values. Okay, so this is the probability of Faraday cage. Okay, and now if when these two probabilities have been taken, so according to the formula x into y, the overall probability is 0.353. So this is all according to the formula that we have seen in the domain attribute section. So the since these are 0, so the probability of block tag reader is equal to the probability of 0.353. Okay, if we assign these probabilities, then according to the formula of probability, the probabilities will definitely will change. So as you can see, the probabilities are changing. Here also we have just assigned the random numbers. Now if I change the value here, the value of the isolate network will change, and according to this the jamming signal value will also change. Now for now, the overall probability of the graph is the attack is 0.843 for blocking communication. So if I change the value here, then the probability will definitely change. Okay, so this is how we evaluate the probability of success. Okay, we can also try different other attributes. we can also estimate how what will be the overall maximum power consumption. We can just check out here. Right. The maximal power consumption, it can be based on the resources, the CPU, etc. So that is also the scenario based, that what all devices are taken into account and what all power consumption and energy constraints are taken. So, the default value for the power consumption is infinity. That is, maximal power that can be consumed is taken as infinity. So suppose we is put some value here, it's 20. Okay, and if it is 20 here, okay, so total value, total power consumption for being in the vicinity of the tag will be 40. Similarly, if we want to insert a Faraday cage, so here, if the power consumption for cage around reader is 56 and cage around tag is 45, then the power consumption here is 56, because this is the OR operation and the maximum of both the powers are taken into account. Okay, now this is, since this is AND operation, then both of them are added and the total power consumption is comes to be 96. Similarly, we can do with all the other nodes, and since secure warehouse we inserted 20, here it is, the value is 20. And like the probability, if we insert different values here, we will get some output, and the every node will keep on changing according to the evaluation strategy. So the power consumption here is 56. Okay, so 56. So overall power consumption of this attack tree is 96, because there is no AND operation, so maximum of the two values is taken, and if there is an AND operation, then both the values are added and the final power is calculated. So this is how similarly we can evaluate other we can evaluate our graph based on other domains. We can also insert our domains in the same way, and we can make evaluations of the graph. In the windows, we can have message log windows. This is the message log window. That new attack defense tree has been created. We loaded an example tree. So this is basically the logs which have the of the actions that have been performed. Okay, and if we want to say valuations view, that proponent being in the vicinity, this shows the assigned value of the probability that has been assigned. And then if we want any ranking view, then we have the ranking view, but this is not implemented on this tree, so this is always based on the attack scenario and attack trees. If we have a different kind of tree, we can use this functionality. So this is all. We can create different other trees according to the scenarios, and we can evaluate, and we can obviously make us some good defense strategy for future, so that there is no loss for the organization. And we can save this tree. We can export to XML file or an image. Here I have saved a few trees. We can check in the pictures. Here we have this tree. Okay, so this is all about attack trees.